So this doesn't just happen in simulations and cool videos that I like to show to people. Indeed, we can actually see this in telescopes. So this is what we call the field of streams, and it is from the Sloan Digital Sky Survey, and it's a picture from 2007. We have updates to this since then. But basically, the colors of these stars are by distance. So you can see here that we have this GD1 stream, the Orphan stream, but especially this really, really thick one is the Sagittarius stream, which is coming from this Sagittarius dwarf galaxy that's just getting ripped apart by the Milky Way. So some of these are actually what we call the globular clusters, which we're not going to have to worry about. But Sagittarius is indeed a dwarf galaxy. So it is indeed a galaxy that has formed outside the Milky Way and is now merging. So which means that it actually does belong to our tree. Just a little bit kind of a history of Sagittarius is that it came in at about 8 billion years ago. And then it did like a first encounter here, and then did another lap, coming in again. And 1 billion years ago is the third passage. So right now we have this huge galaxy. This is ours. And then we have like these beautiful rays of stars that are all around us. So these you can actually see with a telescope, which is pretty cool. And I can guarantee you that stars don't just self-align for no reason like this. So this tells us that Sagittarius has come in a little bit earlier than the Large Magellan Cloud because it's already on its third passage, so it belongs to this genealogy tree a little bit above. Now let's do debris flow. So debris flow is kind of like, it's the least visual thing that we can see, but I like to kind of compare it to long distance running. So this is actually the 400-meter race, a women race back in the London Olympics in 2012. And what I want you to see is that the athletes are actually kind of aligned right here in the beginning. So you can see them as a line. So you can think of that as the stellar stream. After a while, after a few laps, we will not be able to see actually this line, right? So as the video is progressing, and you can see them going, and then I accelerated just because in the middle part nobody cares. But at the end of the day, we can see like a group of people that are just that have lost like that initial structure, but they're all coming in with some velocity and some velocity spread. So that's kind of the way that I think about debris flow. It's basically like a bunch of stars that, although you can't really see the physical structure, they have a very specific velocity and some spread to it, right? So that's what debris flow is. And this is allowed by the Gaia space mission. So in 2013, the European Space Agency has launched this Gaia Space Telescope, and it has since given us the positions and velocities of over 1 billion stars. Actually, the latest data release is 1.5 billion stars. To put this in perspective, the mission right before, which was Hipparchus, that ran from 89 to 93, had only about 100,000. So you can see where if you go from 100,000 to over 1 billion, your mathematical tools or analysis tools really have to keep up because you can't just stare at things anymore. The cool thing is that you could stare at things just one more time, because if you make a plot from the original data set, we found that there is evidence for this debris flow that is called Gaia Enceladus, and basically that there is this galaxy that has merged into our Milky Way about 6 to 10 billion years ago. Enceladus is a Greek godson of Gaia, so it's beautifully fitting. So again, you can see I'm obsessed with videos. Let me show you what happened when Gaia Enceladus came in. So this is Enceladus. It comes in, and you can see it disrupting the stars from the Milky Way, and then settling into this long kind of structure. And you can imagine that the sun lives about here. So actually all around us, there are these stars that we figured out because of Gaia that have very funky kind of velocities that people just like literally made plots, their initial plots, and were like, whoa, something stands out here. And indeed, it's because it dominates so much that this was somewhat of an easy discovery. Well, it's a great discovery, but still easier to find. So that is the Gaia Enceladus that has merged in quite a long time ago. So I went through these a little bit quickly, but basically the Large Magellanic Cloud, if you're in the southern hemisphere in a really dark night, you can literally see by eye. Like you look up in the sky and you can see it. It's incredible. We needed a little bit more progress to see Sagittarius. That's correct. So basically we needed something like the Sloan Digital Sky Survey. So we needed some telescopes and trying to understand kind of the distances and everything. And we could do this in 2007. So Gaia Enceladus, that's true. We could not have seen it coming until we had velocity measurements of these stars, which are very, very difficult to make. But now that we have this wonderful kind of Gaia space mission, that one was literally like you take your data and you plot it and you make a very simple cut and then it just screams at you. You can literally see it in your plot. That's true. You can't see it in the sky, but you can see it in the plot. So basically the way that I think about it is that we've kind of exhausted all the easy way out kind of parts of the Milky Way. And the question is, how can we find the rest? Things that are not obvious. The things you just can't just like squint a little bit and be like, I think there's something there. And this is where machine learning actually comes in. So basically what we want to do is automate the search and that identifies these stellar substructures, the things that stand out from, the stars that are born in the Milky Way. Like the sun, for example. The sun, a lot of people are doing a lot of detailed studies of the sun, but from my perspective, it's like very boring star because it was born in the Milky Way, didn't go very far, about 5 billion years ago, which is like literally yesterday in astrophysics. But what we want to know is stars that have merged somewhere else. So this is what I usually call immigrant stars, basically just like me. So stars that are born in a different galaxy and came in, because they really tell us about the history of our galaxy. So in the remainder of the time, I'm going to go touch through 3 different ways that we've been doing this. One from supervised learning, and then unsupervised learning, and then anomaly detection. So different machine learning techniques to literally dive into this billions of stars in data and figure out exactly where these immigrant stars are. So let's start with the supervised learning. Basically, the trick is to really identify these mergers. You need to identify the stars that have different kinematic properties or chemical properties from the other ones. How to identify members of the Milky Way merger tree? You need to identify these immigrant stars. So I wanted like a little bit of a review, like a short review of stars in the Milky Way. This is the sun, by the way, not to scale, but just to tell us where we live. So first, there is the bulge. So the bulge of the galaxy, it has like a bunch of very old stars, and the way they move is like really around that bulge. They don't go very far. They're very old. It kind of formed with the very early parts of the Milky Way. Disk stars, like the sun, are just kind of in these mostly circular orbits. They actually go up and down a little bit, but they're very young, a few billion years old. And again, these are stars that are born in the Milky Way just more recently. The stars that we're looking for are what we call accreted stars. So these guys. These guys, because they came in from somewhere else, they're not bound to a disk, they're not bound to anything, so they can do whatever they want. Well, under the gravitational potential of the Milky Way. But basically, they have very different kinematic properties. They move very differently from the other stars. The only problem, though, is that around us, there are only about 1% of the stars close to us. So most of them is 99% of these disk stars that we, in this particular aspect, don't really care about. So it kind of puts us in a situation of needle in a haystack, and we're trying to find what these are. The way that we do this, and usually if I have time, I try to mess with people and try to get them to guess which one is simulation and which one is real. Astrophysicists can find it pretty easily, especially because this is the Large Magellanic Cloud. I usually hide it when I try to be a little bit sneakier. But basically what we do is, from the simulations that I showed you earlier, where galaxies actually merge, what we can produce is synthetic surveys, which means that answering the question, if Gaia lived in this simulated galaxy, what would it look like? And that's where we put our cells, and then we can generate images just like that. And we can use these tools to actually train code to distinguish stars that are accreted, so stars that are born somewhere else, versus the stars that are just really boring and part of the Milky Way. So basically what we do is train on simulations and then label the Gaia stars. So basically, we kind of have two labels. It's either a tracer star or an accreted star versus a disk star. And the information that we are taking in is the positions and the velocities. And some people probably have done a lot of convolutional neural networks. So they basically kind of like you throw this into a neural network, and it tries to kind of go through multiple hidden layers and then make some output about how to label these stars and learn some properties of the stars. But in simpler words, it's the way that I think about it is just like, you know, this is a cat, this is a dog, figure out which one's which later. And what we could generate is actually a catalog of these stars that are these wonderful special stars. And we can just do these plots to try to figure out what's going on. So we don't have to dive really into the details of these plots, but basically, the first thing that you can kind of see here is that, so what I kind of did surrounded like in blue is that Gaia Enceladus, that big merger. It had to be there, otherwise I would have had a bug. The halo we knew, but the interesting thing that came out when we were doing this with my collaborators back in 2019 is that we did not know what this is, that purple thing on the top right. And the cool thing in astrophysics is that if you, well, after a lot of anguish and, 3 weeks of self-doubt and where did I go wrong and somebody must have seen this. Anyways, after all of that, you realize that, oh, you're the first person to actually see this. And then you get dibs on naming it. So this is Nyx, the Greek goddess of the night that I'm very proud of. So basically, it's a collection of stars that go very close to where the sun is, but they orbit a little bit differently. So for example, instead of turning like the sun around the disk, they actually kind of go in a little bit, and they are extended a little bit over the galaxy. So these are very interesting. And the cool thing is that we would not have been able to see it without these AI tools. So basically, because it was hidden literally under this mountain of background, and that's why this is so incredibly powerful. Some people say, well, maybe your AI thing is just learning something from the simulations and stuff. But then the reason that we know that this is true is because the AI part just really helped us identify these stars. After that, we just took just this collection of stars. We tried to study their kinematics, their orbits properly, and then we went to observe them with telescopes to try to figure out their chemical abundances. And they are indeed different. It's just that we would not have been able to see it without these tools. So the question still remains whether or not it's part of the Milky Way. And that's a long story that maybe someday we'll talk about. But basically, whether or not it was stars that are born in the Milky Way but got a kick that kind of changed their orbits, or is it something that's coming out of somewhere else? So that's why I leave the question mark in there. We can go a little bit deeper, looking at clustering. So if you don't trust simulations, something that you can do is just take the data very agnostically, don't look at any simulations and say, okay, can I put like basically an algorithm that just separates things into groups and then tells me which group is which. So clustering is basically just grouping, right? Grouping by a certain property. The cool thing is that our brains are actually really, really good at grouping things. The only problem is that we're only good at grouping things in 2 dimensions. So for example, if I show you this, you can already say, oh, this is one thing, this is another thing, there is here, this is a bump, something, and then there are like just scattered of things that just don't belong really anywhere. So the trick about clustering algorithms is that you really need to pick the right algorithm for your data set. And the example here is, for example, if you pick something that is something like k-means, you can see that with the colors that you're like, wait, my brain would not have put it that way, right? Because Why is that brown thing related to that line? That doesn't really make sense. And then, again, there are some very detailed studies to figure out exactly what works with your data. But in particular for us, in this particular context, something called HGB scan clustering or hierarchical clustering actually works best. And it kind of does reproduce exactly what your brain does. The reason that we need to do this is because we are going to move from 2D, right? You can just stare at it. So HGB scan, it was great for us because it allowed for different sizes, it allowed for noise, arbitrary shapes, and densities. And we're not the first ones, obviously, to use this algorithm because it has been known in computer science for a long time. What we wanted to do is use it to cluster our Gaia data. However, the problem that shows up in physics and does not show up in computer science is measurement uncertainties. So our data points have error bars. That's honestly the essence of physical sciences. And this is kind of where the difficulty is. So we can't, that's why I think the conversation between physicists or astrophysicists and AI experts is so critical, because we can't just like use off-the-shelf things and just apply them to our data just because we have some other constraints that are not really, that are not as common in computer science, and in particular measurement errors. So what we wanted to do is use this for measurement uncertainties. So basically what we ended up doing is cluster the first data, shake everything basically based on their measurement uncertainties, cluster it again over and over and over, and the subset that we ended up with is the most stable clusters. So what are the clusters that will always show up no matter how much you shake it? You shake your data within their measurement uncertainties. So this is possibly incomplete, but kind of at least a step in that right direction of trying to incorporate these uncertainties. And finally, and I'll talk a little bit faster, what we can do is look for a stream finder. So I was talking about streams earlier, like they're beautiful things in the sky. The fainter ones are harder to see, right? So what we can do, and basically a goal to understand like the properties of the Milky Way, is to really increase statistics of these stellar streams. And to find them, what we need to do, what has been done, honestly, until very, very recently, is literally just like getting your data, making some cuts, staring, okay, maybe this is something, running their orbits and trying to do it. So it's very kind of like, it's a very sluggish process. So what my collaborators and I actually tried to do is build an anomaly detector, which is kind of takes kind of like the distributions in multiple dimensions and try to kind of extrapolate the background. And if anything stands out, that's what kind of like it says, ooh, there's something here. And then we added some properties to it, which is basically trying to make sure that it's a linear structure, just like that one. And the interesting thing is that early last year, we have about 102 new stream candidates. And we ran this on simulations to figure out like a false positivity rate. So we think that 90 of them are expected to be real. It's just that now we have to actually follow up on them one by one and figure out exactly what's going on. So what I would like to actually kind of end with here is that there is a limit to what humans can do, in particular in this wake of giant data. And AI is really the tool to do it. It's just that we have to be very careful to make sure that it takes into account the properties of the data that we have, and in particular, measurement uncertainties and also the symmetries of the problem. So, for example, like we know that physics respects symmetry. Like if I turn the galaxy around, it should actually kind of give me the same results, etc. So, yeah, on that note, I'm going to leave you with Nyx. This is the Greek goddess of the night coming out of the Milky Way. Thank you. Yes.
Well, first of all, that's a great talk, and I'm really happy that we were able to have your laptop.
I know, the videos, right? Would have been very boring otherwise.
So actually, this is just a comment, fascinating. When you are talking about clustering,
yeah,
with error-prone measurements, I don't know if you're aware, but there is the entire field of bioinformatics and also in public health, where what they do in bioinformatics is try to do three-dimensional approaches for clustering gene expression where the measurements are affected by error.
Oh,
And
interesting.
so and in terms also of the scalability of the problem,
Right.
it's very similar. And so that's made me think about that there is actually a point of connection in data science. So I don't know if you know Rafael Irizarry as one of the name, but there is so much work in trying to figure out. I'm not saying they've solved the problem, but I'm saying that there is an interest, tremendous interest in data science to identify clustering techniques with massive amount of information.
Right.
Then there is measurement error. And with genes, it's a classic example because it's the same scale in terms of dimensionality. And when you are thinking about, do you want to cluster genes so they are co-regulated?
Right.
And the regulation and their gene expression is measured with error. So just want to point it out that could be an interesting place.
I'm going to find you in the break because I do want to actually read those papers.
I can give you some, some of the people, but that's exactly what data science is about, is trying to bring, data science problem with people that, try to face the same challenges.
Absolutely.
So anyway,
Yeah, thank you. That's right. Hi.
Enjoying that discussion because I agree with Francesca.
Yes.
Plenty to talk about. But I have a question that's for you and Matt. Okay. So Matt, you just heard Lina say that she has to follow up on 90 something, whatever, candidates. So do you both think that this amazingly creative, wonderful AI of 2 years from now is going to do that for her?
Oh, those 90... No, unfortunately, no, because some of them we have to actually write observing proposals and we have to send somebody to the telescope to actually watch
So
it.
we're going to have AI observing proposals, AI decisions on the observing
AI writing
They can write the observing proposals.
building
That's right.
experiments, building telescopes, not
Yeah.
50 years from now, definitely.
Yeah.
Right, so, but I
think
mean,
it's
really give
a great
serious
topic for
questions.
discussion for the panel.
Yeah, it is.
So maybe we'll take one more question for Lina and move on.
But it seems that the underlying theme here is the extent to which AI is qualitatively changing astrophysics and then other physical sciences. Could you comment a little bit on the extent to which astrophysics has fundamentally changed? That is to say, are researchers disadvantaged by not using it? Namely, you've discovered things that typical methods have never found before.
Right.
So is it necessary, in fact, to use AI in order to be, let's say, competitive and extend knowledge of astrophysics?
I think for this particular field that relies so much on analyzing data, absolutely. I think it's definitely a very, very strong advantage to be able to do this. I would not say that AI is going to replace humans, though, because you still need that field expertise to kind of distinguish from what's just nonsense versus something that is real, and you have to follow up on it, and you have to really understand kind of like the theoretical background that's still done by humans. But I think definitely for astrophysics, or at least like, especially because the field of astrophysics has an explosion of data, especially this decade, right? From the Gaia space mission, JWST, that kind of came online a couple of years ago now, and Euclid that came online like a few months ago, and then we have like a few actual space missions that are gonna come online like in the next couple of years. I think the Rubin Observatory should be on either later this year or early next year, where it's gonna have like terabytes of data a night, where it's just at that point there is no way you can kind of get around it. So for that area of astrophysics, it's absolutely critical. There's no other way.